Learn the art of optimizing GPU scheduling in Kubernetes for efficient resource management. By the end of this video, you'll master configuring and optimizing Kubernetes clusters for GPU workloads. Welcome to our deep dive on optimizing GPU scheduling in Kubernetes. Did you know that efficient GPU utilization can drastically cut costs and enhance performance in data-driven environments? In this video, you'll learn how to configure and optimize your Kubernetes clusters specifically for GPU workloads, which is a crucial skill for IT professionals and developers aiming to leverage high-performance computing. Let's get started. When it comes to managing GPUs in Kubernetes, understanding resource requests and limits is fundamental. Resource requests determine the minimum resources guaranteed for a pod, while limits cap the maximum resources a pod can use. Proper configuration ensures that your applications have the resources they need without overwhelming the system. Failing to set these appropriately can lead to inefficient resource use or even system crashes due to resource contention. We'll explore how to define these parameters in your pod specifications and best practices to follow for optimal performance. Node selectors are a key component in optimizing GPU workloads in Kubernetes. They allow you to specify which nodes a pod should run on, ensuring that GPU workloads are assigned to nodes equipped with the necessary GPU hardware. This is crucial for maintaining compatibility and performance. In this section, we'll walk through the steps of configuring node selectors in your Kubernetes setup, ensuring that your workloads are efficiently distributed across available GPU nodes. Taints and tolerations are powerful tools in Kubernetes that help prevent resource conflicts and ensure that workloads are strategically placed. Taints are added to nodes to mark them as tainted, which can only be tolerated by certain pods. This mechanism is particularly useful in scenarios where you want to ensure that only specific workloads run on certain nodes. By leveraging taints and tolerations, you can reduce system bottlenecks and optimize GPU scheduling. We'll discuss practical examples and guide you through setting this up in your Kubernetes clusters.
Device plugins in Kubernetes play a crucial role in simplifying the management and discovery of hardware resources like GPUs. These plugins automatically discover and allocate GPUs to applications, reducing the complexity of cluster management. In this segment, we'll explore how to install and configure device plugins to enhance your Kubernetes environment. This setup not only streamlines GPU resource allocation but also ensures your clusters are running efficiently, maximizing your hardware investments.
Resource quotas in Kubernetes are essential for managing and limiting resource consumption across namespaces, particularly in multi-tenant environments. By implementing resource quotas for GPU usage, you can ensure fair distribution of resources, preventing any single user or application from monopolizing GPU capabilities. This section will guide you through the process of setting up and managing resource quotas, helping you maintain balanced and efficient usage across your Kubernetes clusters. Effective monitoring of GPU usage is critical for maintaining optimal performance and efficiency in Kubernetes environments. Prometheus and Grafana are powerful tools that provide real-time insights into your system's GPU usage. In this segment, we'll cover how to set up Prometheus for data collection and Grafana for data visualization. With these tools, you'll gain the ability to track usage patterns, identify bottlenecks, and make informed decisions to enhance your cluster's performance.
Scaling GPU workloads effectively in Kubernetes presents unique challenges, but with the right strategies, you can ensure your system meets growing demands. This section focuses on best practices for scaling, including automating workload adjustments and balancing resource demands. We'll also explore horizontal scaling techniques and provide case studies that highlight successful implementations. By the end of this segment, you'll be equipped with the knowledge to scale your GPU workloads efficiently, maintaining high performance as your demands increase.
Learning from real-world examples can provide invaluable insights into GPU scheduling optimization. In this section, we'll examine case studies from leading companies that have successfully optimized their GPU scheduling in Kubernetes. We'll discuss the challenges they faced, the strategies they implemented, and the outcomes they achieved. These examples will highlight best practices and demonstrate the tangible benefits of efficient GPU scheduling, offering you practical guidance for your own implementations. Congratulations on reaching the end of our session on optimizing GPU scheduling in Kubernetes. We covered key strategies from setting resource requests to implementing monitoring solutions. Remember, efficient GPU scheduling is not just about performance, it's about cost effectiveness and maximizing your hardware investments. We encourage you to implement these strategies in your Kubernetes clusters and share your experiences in the comments below. Don't forget to like, subscribe, and let us know what topics you'd like us to cover next.